Welcome back to our lesson practice review, where we're talking about chapter 3, lesson 8, where we factor some more challenging polynomials here that we're going to be dealing with. I will rely heavily on our box diagram to help us with these. There's like 3 different instances that we need to be prepared for that we'll kind of go through. One of them is seeing things with higher exponents than just 2, even though normally we're just used to using the box for quadratics. We can use them for some other ones that we will kind of see here in this review. So for problems 1 through 3, rewrite each polynomial as the product of 2 factors. Again, it's just asking us to factor, and it lets us use a diagram if it helps. And I usually like to. The one situation that I don't feel like I really need it is a of x here, because this is what we call a difference of squares. So I'll show you in the box here what kind of happens here, but we know that the first term goes in the first box, the last term goes in the last box, and then what we normally have is this middle term, but since there's no middle term here, I know that these 2 boxes have to cancel out, which the only way to do that is when we have a difference of squares here, that this has to be 12 and this has to be 12, and then only one of them has to be negative, because when one of them is negative, that's what makes this term the negative version of this term, canceling each other out, giving me just 49x to the power 4 minus 144 in there. So this is a difference of squares, which again, oftentimes when I do these problems with 2 terms, if I can notice that it's a difference of squares, meaning it's subtraction between these 2 terms, and those 2 terms are perfect squares, I know it's the square root of the first term plus the square root of the second term multiplied by its conjugate, or the square root of the first term minus the square root of the second term. For number 2, I definitely have to use the box on this one here. Same idea, where first term, first box, last term, last box, and this middle term, 2 things need to multiply into 30x to the power 4 that multiply into negative 11x squared, which would be negative 6x and negative 5x. And so, sorry, those are now squared. So that's the little bit of difference here, is that I'm dealing with power of 4. So both of those are going to be squared, which means that this has to be 3x squared, this has to be x squared, negative 5, and negative 2. And so when I factor this, 3x squared minus 5, x squared minus 2. And so this is kind of why they use these long terms of saying, hey, use the they use this long term of rewriting each polynomial as a product of 2 factors, because technically if it just said like, hey, factor it, there are going to be times when we have these kind of more in-depth problems, like to the power of 4, that once you factor it once, maybe you look at this and you can see that it can be factored again. And so right now it's only asking us as a product of 2 factors, so I'm just going to do this first step here and call it done. For number 3, we got 4 terms, which I can still use the box here, because normally I have only 3 terms and I have to split that middle term up into 2, but this middle term, there actually is already 2 of them. So I can just put those 2 terms into these 2 boxes and start figuring out what goes where here to multiply into these values. And so this one here actually does factor. Again, that box doesn't always work because the polynomial that we're given isn't always factorable, but in this case here, we have one that works out nicely as x squared plus 2 and x plus 5. All right, for number 4, we got 2 representations of p of x here. We have its factored form, and then we have what the graph ends up looking like here. And so when we're looking at this one here, it asks us to determine how many non-real zeros there are. Well, a couple of things about this that we could use to help us. First of all, we could just solve it if we wanted to, right? Set them equal to 0, use the 0 product property to set each piece equal to 0, and I'd see that I'd get one real solution, and I'd end up getting the square root of the plus or minus 2 non-real. So that's definitely one way. Another way we can use is if we're given this original function and we see that it is a 3rd degree polynomial, and then we see that it only crosses the x-axis one time, Well, that means that the other two x's do not cross it or give us non-real zeros. So again, this one solution that gives us a real solution, that's where we see our x-intercept, which means that the other two x's have to be giving us non-real solutions. All right, problems 5 through 7, determine the zeros of each function. Use a diagram if it helps. I think I will for some of these. Again, on this one here, I'm going to use what I know about a difference of squares because these are both perfect squares. Square root of the first plus the square root of the second. Square root of the first minus square root of the second. And here's what I was talking about earlier is that normally we can be done factoring here. I actually know that I have another difference of squares here. So I could x squared plus 16 and then change this into a difference of squares and make this a little bit easier on myself. So it's not required, but that is one way of doing it because then I need to set them equal to 0 using the zero product property. X squared plus 16 equals 0. Subtract 16 from both sides, take the square root of both sides, and get x equals plus or minus 4i. So that's two of our solutions from here. Then I set x plus 4 equal to 0 and x minus 4 equal to 0, which gives me x is equal to negative 4 and x is equal to positive 4. So in this one, there are 4 zeros. We got x equals 4, negative 4, 4i, and negative 4i. And sorry, I'm a little bit cramped here on space. Again, I wish they had given us more space on questions like these, but we'll deal with it. The second one here, I guess number 6, I'm going to go ahead and use my box here, x to the power 4, negative 36, and then the middle term, negative 5x squared, needs to multiply to negative 36 to the power of 4, which would be not 12 and 3, but 9 and 4. So we got negative 9x squared and 4x squared. And so this one here, x squared and x squared, negative 9 and 4. So this now factors into x squared plus 4 and x squared minus 9. Again, the way that I like to do this is factor it as much as possible. So I'm going to make this into its difference of squares of x plus 3 and x minus 3. I set each of these terms equal to 0. And sorry that I'm cramped here, but subtract 4 from both sides. Take the square root of both sides to get plus or minus 2i. And then x plus 3 equals 0. X minus 3 equals 0. And I get x equals negative 3 and x equals 3. So for number 6, my answers are x equals 3, negative 3, 2i, and negative 2i. And for number 7 here, I'm going to use my diagram again to factor. And in this one, since I have 4 terms already, I'm going to see if it factors nice and pretty. Since 4 terms go into 4 spots, 3x squared, 9x, and 27. X squared, x, 3, and 9, it does. So it becomes x squared plus 9 and x plus 3. Set each of those equal to 0. I'm getting sloppy here, sorry people. Negative 9, take the square root of both sides to get plus or minus 3i. And then this one here gives me negative 3. So my solutions are x equals negative 3, positive 3i, and negative 3i as my zeros. Okay, for number 8, which graph represents the function f of x equals 2x to the power 4 minus 32? So first of all, the degree is 4, which means both the left and right side have to point up because it's positive. So I know already not a, because that's a cubic function. The next thing, when I'm looking at this, I need to kind of imagine what the zeros are going to be. And there's a couple ways I could do this. Since I know that the zeros here are given to me, I can kind of see we have 3 of them here and 2 of them here and 2 of them here. I could just plug in those numbers to see what I end up getting. The only reason that doesn't work for sure is that it looks like B and D both have the same zeros. One of them has a multiplicity of 2 for each of them. The other one does not. So what I'll do here is I'll actually try and factor this to see kind of what it looks like if I get those multiplicity of 2 or not. In this one, I factor out a 2, which gives me x to the power 4 minus 16, which that's a difference of squares, so it becomes 2 x squared plus 4, x squared minus 4, which again, another difference of squares here, so I get x squared plus 4, and x plus 2, and x minus 2. And so once I factor this, I see that there are only 2 real zeros here, and positive 2 and negative 2, and they both have just a multiplicity of 1. So it's not going to be D and it's not going to be C because there's only 2 real solutions. So I know that it has to be B. For number 9, change one factor of the function f of x equals x squared plus 25 times x minus 3 squared so that it has 3 intercepts. Right now it only has 1. And so this one here gives me 2 non-real solutions. If I wanted to make it 2 real solutions from this, all I have to do is change it into x squared minus 25 because that's a difference of squares, giving me x plus 5, x minus 5, and now I have 3 intercepts, one at negative 5, one at positive 5, and one at positive 3. Moving on to our spiral review. Problems 10 and 11, factor each quadratic function by completing the diagram, then identify the zeros of the function. So in this one here, to find out my middle term, it looks like first term went in the first box, last term went in the last box. That middle term of positive x needs to split up into 2 things that multiply to negative 20x squared. And so in that one, I would say that would be 5x and negative 4x, which means this has to be negative 4, this has to be 5. When I set that equal to 0, I end up getting my 2 solutions of negative 5 and positive 4 because I use the 0 product property and set each of them equal to 0. All right, number 11, same idea here. First term, first box, last term, last box, middle term of negative 9x. Those 2 pieces have to multiply to 8x squared. So that would be negative 8x and negative x, which means that this has to be negative 1, this has to be 8. And using the 0 product property, x minus 1 equals 0, x plus 8 equals 0. I get my solutions of positive 1 and negative 8. That wraps up our lesson 8 practice, and hopefully we feel comfortable with our new factoring. I think the main kind of things to focus on are difference of squares, and then being able to factor something that has a power of 4 using that same diamond and box idea, or maybe a 4-term polynomial where we throw it into the box.